Welcome to this seminar. And in this seminar, I wanted to have a look at some periodic or quasi-periodic influences on Earth's biosphere. So these are things that might impact us in the future, things that have happened in the past, things that are going to happen in the future, things we might be able to predict. And your aim really is then to see how we might tackle those going forward with our current technology or advancements in technology as we kind of progress. So, you might be familiar with this asteroid here. This one was responsible for wiping out the dinosaurs, I suppose. So, this was actually part of a wider periodic flux, or it likely was. So, we had a large impact millions of years ago, potentially wiped out the dinosaurs, but it wasn't on its own, it wasn't isolated to that, and it could have come as part of a more periodic flux of these type of objects that would have hit the planets. And things like mass extinction events, they're not necessarily random, they don't just randomly occur. If you go back in time and look when they've occurred and how often they occur, there does seem to be some kind of pattern to them. There is some kind of periodic fluctuation to those impacts that are actually occurring. So here you've got some examples of mass extinction events, and they're not randomly distributed. There is some kind of period there to when they're occurring. So this is just an example of mass extinction events. And these actual periodic fluctuations are not just in the extinction records, which actually, to be honest, are quite recent because we have access to those. We can go further back in time. We can look at the climate of Earth. We can look at impacts as well that didn't necessarily relate to extinction events, but we can actually look at more geological records, and we can still see those sorts of periodic fluctuations in all of those sorts of records as well. So the first thing we really want to cover is Milankovitch cycles. Now these are actually quite short periods. These are only on the order of thousands of years typically, whereas the ones that I was referring to with the dinosaurs, the asteroid impacts, those can be on the order of millions, hundreds of millions of year cycles instead. So we have a different range of timescales essentially where these fluctuations or periodic fluctuations can occur. Now Milankovitch cycles are quite short term, really. They probably have the biggest effect on us because a few thousand years is a much shorter time frame and something we can probably work towards kind of not necessarily solving, but we can adapt to them. So what are the Milankovitch cycles? Well, they relate to Earth's orbit, and Earth's orbit essentially defines its climate. It currently sits in the habitable zone, and hopefully it will for some considerable time. But if you change the orbit of Earth, it's going to either get closer or further away from the sun, or it gets more elliptical. That changes your seasons. So it predominantly comes down to the orbit of Earth with regards to the Milankovitch cycles. You change that, you change the climate. So we know that actually the climate's been found to change in the past. And this could relate to orbital changes. It could relate to other factors as well. But we do know that the climate in the past has changed. So we've gone through kind of snowball Earth. It's then warmed back up again. And again, there does seem to be possibly some quasi-periodic fluctuation there between getting hot and cold. Not necessarily always related to Milankovitch cycles or orbital changes, but there are some changes nonetheless. So where's the evidence of this climate change? Well, we can drill ice cores, so we can go and get really deep cores of ice cores where we can get records of the past climate basically. So when the snow fell back then, we can get records of that, what the atmosphere was like, what the temperature might have been like. You can also do similar sort of things for deep sea sediment cores. You can go deep back in time looking at those, and you can get records of what the climate might have been like at certain times. So we've got a reasonably good idea that the climate has been fluctuating and changing in the past. And here you've basically got your atmospheric concentrations here and your temperature. So you've got carbon dioxide at the top there. You've also got temperature anomaly there. And again, it's somewhat noisy, but it also potentially, if you were to run a Fourier transform on that, you'd probably pick out some key frequencies, some key periods there. And that's a key part of these actually, that when you look at the data like this, it doesn't necessarily jump out straight away that there's some period associated with that. But if you, again, looked at the power spectrum of that, took the Fourier transform, something along those lines, you're likely going to start picking out some key frequencies, which is important. So we then expect that orbital changes is then going to drive our climate changes. So the first one then, Milankovitch cycles, is cycles in eccentricity. This is where the orbit of Earth gets more elliptical and then more circular, and it typically occurs on a time frame of like 100,000 years. So we go through a cycle every 100,000 years, and it gets more elliptical, more circular, more elliptical. What does that actually mean for the climate? Well, what it does is it drives more extreme seasons. Now, things like the semi-major axis is independent to eccentricity. So this semi-major axis is like the orbital radius. So we're not making Earth closer or further away from the Sun. So overall, average-wise, it will be the same distance. But if you make it more elliptical, it means that the extreme points of its orbit, it gets closer to the Sun, it gets further away. You then can get more extreme seasons as a direct result of that due to this first Milankovitch cycle. We then also have tilt. So Earth's tilt can cycle between about 22 and, well, just under 25 degrees every 41,000 years. This again causes your season to become more extreme, and it fluctuates between that sort of angle there. So we get this actual tilt that fluctuates as well as the actual orbit itself. And we also have precession of that axial tilt as well, and that's on a shorter time frame of just under 26,000 years. Now what happens here is the seasons start at different times, and you get a larger difference in temperature between each hemisphere. So again, kind of relates to your seasons here as well. It changes when they occur, and then you get larger differences between your north and southern hemisphere because it kind of fluctuates. And you have to think of these things as like a spinning top, basically. So if you've got a spinning top, as it slows down, it begins to wobble. Same sort of thing is kind of occurring with Earth, really. And also, if you were to change the mass distribution of that spinning top, you can change how it actually rotates and spins as well, which we'll come back to, and does directly relate to us as humans and our activity on the actual planet. And then we also actually have precession of the orbit itself. So the actual elliptical orbit will precess around the Sun, and that takes, well, over 100,000 years. So about 112,000 years it takes to go through one cycle, where it precesses around like this here, as you can see. We also get cycles in inclination. So about every 100,000 years, again, we have the inclination will become more inclined, and then it will come back down to the orbital plane again. So it kind of cycles, more inclined, less inclined. And again, that can obviously alter things like your seasons and that, how much energy is falling onto the planet and that sort of thing. So we get inclination cycles every 100,000 years. And basically, inclination and your eccentricity, your periods are around about 100,000 years. And interestingly, that kind of matches the glacial cycles we have on Earth. So when we go look at things like our ice cores, we look at the actual temperature of the Earth, they seem to be cycling on the order of hundreds of thousands of years, which seems to match up and line up with oscillations in our inclination and our eccentricity, which is quite interesting. So we know those cycles occur in orbit. We know they actually occur in the glacial cycles as well. So we possibly have a cause there relating to why they're occurring. Now, what's actually driving the cycles? So we kind of know that they're occurring relatively well. We can measure that. We can predict it with models and stuff like that. But where are they actually coming from? Well, it's interactions with other planets, specifically things like Jupiter and Saturn. They all have different orbital periods. They're not in any kind of resonance at the moment, but you do get perturbations from them, and that can drive it to be more elliptical and then less elliptical. And they occur on quite long time frames, basically, but it's down to interactions with other planets potentially in the system. We also get tides from the Moon and the Sun, and overall that can then cause cycles in our orbit, in our rotation, and things like that as well. So we've got the moon tugging on us, we've got the sun tugging on us tide-wise, so that can have an effect on these cycles as well. Now, it's not just Earth. Not just Earth has these Milankovitch cycles, other planets have them as well. So, for example, we've got Mars. Mars here also has cycles for its rotational, its axial tilt, its eccentricity, its inclination, things like that, which is also going to affect its seasons, its temperature, climate, things like that. And these oscillate on time frames from like 50,000 years to up to 1,000,000 years. So we get similar sorts of things occurring with Mars. Mars has a different orbital period, a slightly different rotation period and tilt. So they're going to be slightly different to Earth, but nonetheless, we have a similar sort of thing occurring there. So it's not just isolated to Earth. Also Titan. So Titan actually is the largest moon of Saturn, has an atmosphere, has liquid oceans. They're not water, they're kind of methane. But we have 60,000 year cycles which can actually change the locations of those lakes on Saturn's moon, Titan. So even moons around planets can experience similar cycles or climate cycles as well. Again, Neptune's moon Triton, we could be getting migration of nitrogen deposits due to similar sorts of cycles. So again, this just highlights the fact that it's not just isolated to Earth or planets, but also moons as well. So they all kind of go through similar sorts of periodic cycles in their climate, potentially their temperature and their seasons on different time frames. Now, something interesting that is starting to be considered now is external perturbations or interactions outside of our solar system. So I mentioned that some of these Milankovitch cycles are potentially driven by interactions internally in our solar system. That would give us relatively short periods, so on the order of thousands, hundreds of thousands of years, but we can get longer term cycles due to interactions and movement in our own galaxy, the Milky Way. So stars in a disk galaxy typically orbit in a common direction if they're in the disk component. If they're not in the disk component, then obviously they can have more random motions in the halo, but we're in the disk. We're a disk star system basically. So we're orbiting in a common direction with all the other stars. The spiral arms in our Milky Way and other spiral galaxies also orbit in the same direction. However, they're kind of quasi-static in the sense that they're not orbiting at the same velocity as the stars. And you have to think of it a bit like traffic on the road. The cars are travelling down the road, and if people brake in front, all of the cars get closer, and you get a density wave that passes back through the traffic. So that density wave is not moving necessarily in the same directions as the traffic. It's moving at a different speed, maybe different direction, and it's the same thing with a spiral arm. A spiral arm is a density wave. The stars go in and out of the spiral arms, so they're kind of semi-static in the structure of the galaxy. They still orbit around the centre, but they're orbiting slower or faster depending on where they are. And with regards to the solar system and the sun, we're going in and out of spiral arms, so we're kind of catching up and going into them. So what does that actually mean? Well, we expect there's about 200 million years between each arm we go into. So the sun goes into spiral arms approximately every 200 million years. And what we've been working with is looking at the reworking of continental crust on Earth. And there seems to be a periodic reworking of that seems to line up with the time frames of going into spiral arms and going into the next spiral arm. So every 200 million years, or between 180 and 200 million years, we seem to get a reworking of the continental crust of Earth, which goes back to really deep time, to billions of years. So we've got quite a time frame really to work with, and multiple passages through spiral arms. And that could be that as we go into spiral arms, stars get closer, there's a gravitational perturbation on our system, and that can actually send in or destabilize outer objects like the Oort cloud, sends in comets. You get a flux of comets going into the inner part. They have the potential then to impact the inner planets. So in this kind of scenario here, only the long period comets or interstellar objects, these are objects that are not from in our solar system, only those have enough energy to really do this crystal reworking. If they're nearby, like from the asteroid belt, yes, we get hit by those more often, but they have lower energies. They don't quite do the, not necessarily destruction, but they don't impart the same amount of energy into the crust and cause the reworking and remelting. But the long period ones and the interstellar objects are traveling considerably faster, and they can actually impart a lot more energy, which we can then detect in this deep time from the geological records. So these extinction events and impacts are starting to appear periodic, and then you can start to map those onto the spiral arms, which is what we've been looking at. So here you've got the Milky Way, and you've got the direction of the sun going around there, and then overlaid onto that, you've got kind of mass extinction events, and you've also got impacts that we can actually directly detect. And they seem to overlay onto when we're in the spiral arm. So there's something occurring there that is perturbing these outer objects, or we're getting an influx of interstellar objects with enough energy to cause significant crustal damage, I suppose. So what was actually done here to find the crustal reworking was looking at oxygen isotopes, and they showed that there was deep melting, suggesting that the crust was depressed into the mantle. And again, you need significant amounts of energy to do that. Near Earth objects, whilst they hit us more frequently, don't necessarily have the right amount of energy. You can look at your kinetic energy and how that scales with velocity. If you increase the velocity, you increase the amount of energy considerably more. So it's about those very high velocity impactors and the fact that they're causing this crustal depression into the mantle to cause the melting, which we can detect by looking at the oxygen isotopes. So here what was done was looking at those oxygen isotopes, things like that. We were looking at the crystal reworking as a function of time. We then ran a periodogram, essentially a Fourier transform, looking at the power spectrum of that. And there was two locations originally that we looked at, and one of those was the North Atlantic craton and then the Pilbara one. And it showed that there was actually some periodic working there. So what we've got here is the green line is a 95% confidence level, the red line is I think noise, and we can see that actually the black line is the data, and it goes above the 95% confidence line, specifically around kind of approximately 180 to 200 million years. Again, that kind of coincides with our spiral arm passage, potentially. Now, also noted here, there are some other periods that have a fairly strong confidence level as well. And we're working and looking at those that they could relate to other fluctuations in the galaxy. So, for example, going below the galaxy and above the galactic plane gives a gravitational perturbation as well. But on the right-hand side there, you've basically got how these impacts could do the crystal reworking and how it actually pushes it down at the mantle. You then get kind of significant melting of that, which you can then detect. So something else to consider, this is a slightly different cycle, but something that we are also detecting as well, is that the stars are not on perfectly circular orbits when they're going around in the galaxy. They're actually on slightly elliptical orbits, and they move radially in and radially out. Now that is known as the epicyclic period. So the period it takes to do one radial cycle, go in and come back out again, is the epicyclic period. For the Sun, it's approximately 150 million years. And again, we're potentially picking up periods around 150 million years as well. So that radial movement is causing gravitational perturbations potentially on our outer Oort cloud as well. So along with the actual radial motion, we've also got that vertical motion that I mentioned. And if we look edge on at the galactic disk, the Sun is also oscillating vertically. And that's a shorter period of around about 60 million years. But interestingly, the fossil records seem to show us approximately 60 million year cycle in essentially mass extinction events. So we could be seeing the vertical oscillation more locally in time from the fossil records here. So why is it doing that? Well, galactic tides can obviously perturb orbits. You can actually alter planetary orbits. minorly, but you can also alter the Oort cloud objects as well. So they're more susceptible to being disturbed because they're further away from the sun. The tides from the sun are less, and they're more susceptible to external perturbations. Other stars flying by can also perturb planetary systems, and we know that occurs quite frequently. Stars move close to one another, and when they do so, the gravitational perturbation from that other star can distort the orbits of objects in the other one. So we know that actually some of our long period comets have actually been disrupted by stellar flybys on our own system. Now, again, if you actually go into the spiral arms where stars get closer to one another because they are a density wave, you potentially would have more stellar encounters in a spiral arm than you would do outside. You may also just get the gravitational perturbation in general, which would perturb their orbit. So these Oort cloud objects, which are in the outer part of our solar system, can then get knocked inwards, and then they become long period comets, and they go inwards into our inner part of our system. Now, when they do that, they have the potential to cross the planet's orbits. And because they're almost perpendicular to the orbit of the planet, they will impact with very high relative velocities. Near Earth objects, when they cross the path of Earth, it's more of a glancing blow. Whereas when a long period comet is going to hit a planet, it's going to be hitting it almost perpendicular to the direction the planet is moving. So the relative velocity of that impact is greater. So long period comets can potentially then cross planet orbits. Now there's some other things to consider as well that I haven't mentioned here, but these are potentially on other time frames. There are other things that maybe humans have an impact on, and that is the altering moment of inertia of Earth. Let's say we are responsible for melting the ice caps of Earth. That ice that was held at the poles melts, it gets redistributed over the planet. You've changed the moment of inertia. You've changed the way the planet rotates by melting the ice caps. If we build cities, and we build cities just on the northern hemisphere, take material from southern hemisphere, we transport stuff around the planet, we change the mass distribution of the planet. We change the moment of inertia. We can change how the planet rotates purely by building stuff or warming the planet up. So there are other things to consider. We can also, well, maybe not consider this, but the solar cycles occur every 11 years approximately. They're very short term, really considered to what I've considered here. So I haven't noted them really, but we do get 11-year cycles in the sun's activity, which could potentially have an impact on our climate, also on our technology as well. Now, what I want you guys to actually have a think about really is all of those different things that can change our climate, can change the orbit of our planet, even impactors that might come on, like in periodic fluctuations. How can we actually use our current technology or advancements in technology to help protect us going forward? Like if we know we're going to get impacts, what we're going to do? Are we going to go to the asteroid, blow it up? Are we going to divert the direction of it? How can we actually, work towards knowing that our climate is going to change and oscillate on some time frame? What can we do? And here we've actually got the DART spacecraft impacting an asteroid, and the idea of that was to show that we could divert the path of an asteroid if we found it to be a danger to us in the future. And the evidence from that showed that we are able to deviate the trajectory of an asteroid if we get to it early enough and we hit it with a spacecraft. So there are things like that we can consider to protect us from the impactors, but there are other things that we might want to think about shielding us. If we know our climate's going to cool down, if we know we're having Milankovitch cycles or things like that, what can we actually do to help shield us and protect us going forward?